On the night of May 12, 2022, the Event Horizon Telescope Collaboration released the first direct image of Sagittarius A, the supermassive black hole at the center of our galaxy. What they showed the world was a ring of orange light surrounding an absolute void. 4 million times the mass of our Sun, compressed into a space smaller than Mercury's orbit. And what that image revealed about the death zone around it is why I made this video. Sagittarius A is not new. Radio astronomers detected it in 1974, a compact radio source at the galactic center that shouldn't be there. For decades, it was a radio point. Then came the infrared observations. Then the X-ray data. Each wavelength revealed the same thing, a mass so extreme that nearby stars orbited it at speeds exceeding 7,600 kilometers per second. The orbit period, 16 years. The measurement came in 2020 from Reinhard Genzel and Andrea Ghez, the 2020 Nobel Prize in Physics. But the 2022 Event Horizon Telescope image changed what we could measure. For the first time, we saw the event horizon itself, the point of no return directly. Not inferred. Not modeled. Seen. The diameter of that event horizon is 44 million kilometers. If you placed Sagittarius A where our Sun is, the event horizon would extend past Mercury's orbit and deep into Venus's territory. And that is the boundary of the death zone. Everything inside it dead. Everything outside it still falling. The problem is not that Sagittarius A is distant. The center of our galaxy is 26,000 light-years away, safe by any measure of human travel. The problem is that the zone where death becomes inevitable is far larger than the event horizon itself. Astronomers call this the tidal radius, the distance at which gravitational forces exceed the internal binding forces of a star. For a star like our Sun approaching Sagittarius A*, that radius is approximately 1 million kilometers. Hold that number. 1 million kilometers. That is the distance at which a solar mass star begins to die. Not because of heat. Not because of radiation. Because gravity at the star's near side becomes so much stronger than gravity at its far side that the star cannot hold itself together. The difference in gravitational force across the star's diameter exceeds the star's own gravity. The star stretches. It tears. It becomes a stream of plasma falling toward the black hole. This is called spaghettification, and it happens routinely at Sagittarius A. But here is what changes the calculation. Sagittarius A is not dormant. In 2021, astronomers using the infrared array gravity detected flares of X-rays and infrared radiation erupting from the accretion disk, flares indicating that material was being consumed actively, right then. The black hole is not waiting for stars to wander into the tidal radius. It is actively consuming them. And the accretion rate tells us how often. The accretion rate of Sagittarius A is low, roughly 1/10 of a solar mass per million years. That is a rate so slow, it seems almost dormant compared to active quasars, or even other galactic black holes. But 1/10 of a solar mass means one complete star, shredded and consumed, every 10 million years. In the time humans have existed as a species, 300,000 years, Sagittarius A has consumed 30 complete stars. Stars that once had their own planets. stars that might have had their own versions of Earth. The tidal radius I mentioned, 1 million kilometers, is not a fixed number. It depends on the star's size and density. A red giant, bloated and low density, has a tidal radius of 10 million kilometers. A neutron star, compressed to the density of an atomic nucleus, has a tidal radius of perhaps 500 kilometers. This means different types of stars are destroyed at vastly different distances from the black hole. And this means the death zone around Sagittarius A is not one zone. It is many zones, layered by stellar type. The energy released when a star is consumed by Sagittarius A is not trivial. Current models predict that a single stellar tidal disruption event releases energy equivalent to the entire lifetime output of our Sun, and it releases that energy in a matter of weeks. The 2021 flare detected by gravity was one such event. A star encountered Sagittarius A. The star died. The X-ray burst that resulted was visible to telescopes across the spectrum. No organism on that star's planets, if any existed, survived the radiation. One measurement in the infrared observations does not fit the standard tidal disruption model. The accretion disk temperature during the 2021 flare reached higher values than the standard physics predicts, suggesting that either the accretion process is more efficient at heating material than current models account for, or that the incoming stellar material has properties we don't yet understand. I'll come back to this, because what it means changes how we calculate the death zone. We are halfway through, and the next measurement is why I made this video. The tidal radius of Sagittarius A is expanding. Not because the black hole is growing, the accretion rate is constant, but because we now understand that the tidal radius is not just a function of gravitational force. It is also a function of magnetic field strength. And the magnetic field around Sagittarius A is stronger than we previously measured. The magnetic field affects tidal disruption because it can accelerate the spaghettification process. A strong magnetic field can compress material, increasing the tidal stress on incoming stars. This means stars that would have been barely disrupted at the old tidal radius calculation are now completely shredded further out than we thought. The death zone is not shrinking. It is expanding. Stars encounter their destruction earlier than the old models predicted. There is a second expansion we have not discussed. The accretion disk around Sagittarius A is not a thin disk. It has thickness, vertical extent, above and below the equatorial plane. And this thickness means that material being consumed does not fall straight down. It spirals and oscillates. It creates shock waves. These shock waves can, in rare cases, reflect material outward, creating secondary tidal disruption zones at greater distances than the primary zone. The death zone is not one region. It is a structure with multiple layers. And now the detail I held from segment 10. The temperature discrepancy in the 2021 flare. If the accretion process is indeed more efficient than the standard model predicts, then the energy released per unit mass is higher. This means higher radiation pressure. Higher radiation pressure means stronger outward forces on infalling material. Stronger outward forces mean the tidal disruption process can penetrate further from the black hole before the material is completely consumed. The death zone expands again. When we combine all these effects, the magnetic field, the disk thickness, the shock waves, the higher than predicted efficiency, the tidal disruption radius of Sagittarius A extends to approximately 2 million kilometers. Not 1 million. 2 million. That is a death zone, nearly 5 times the diameter of our Sun. And within that zone, no star survives intact. Every object that crosses that boundary experiences forces that exceed its internal strength. It tears. It falls. It becomes part of the accretion disk. And this is happening right now. The 4 million solar masses we started with, this is what that means. The gravity is so extreme that it reaches out 2 million kilometers and says, nothing here survives.